Thank you guys for coming. Welcome to the ELEC3105 Electrical Energy Finals Crash Course. It'll be presented by myself and Jackson. I'm Otto. That's Jackson over there. And yeah, so general overview. We have a attendance form and a set of slides. So you can access these slides at a later time, whenever. It should be accessible via the ELSOC drive too. Yeah. Good to just get it. Yeah. Because we might just glance past a few things that you might want to also take note on. It's a nice summary of the course. And yeah, general structure, we're going to have an overview for topics 2 and 3, small question on transformers, bashing out topics 4, 5, and 6 for maximum relevance for the finals. And yeah, I'll be on topics 2 and 3 and 6, and then Jackson will be king of topics 4 and 5. All right, so let's get straight into it. Three-phase and per unit system. That is what topic 2 was. Rather generally, I mean, we're all the way through the course now. Please, I hope you understand. Three-phase is really just, okay, what if the middle was a 0? That's really all we're thinking of, just by symmetries. Some things to note is typically with power, we enjoy using V phase, I phase equals our total power. Something I might recommend you do, and something you consider, is it's the exact same as just going V line to line, I line to line equals power. Just because we know that a lot of our rated values are in the form of line to line things, so that might be useful. All right. Something to note as well that I kind of skipped. Don't forget to conjugate your current. Very silly mistake. Positive sequence, negative sequence for phase sequences. Positive is just clockwise, negative is anti-clockwise, running ABC. Otherwise, I mean, that's pretty much general content for topic 2. There's not too much more to cover. Per unit system, main concerns would be when you're working with transformers, you have 2 different unit systems on either side of the transformer. Ensure that you are converting to the relevant base, right? All right, topic 3, transformers, going straight into it. We haven't seen a lot of core type or shell type questions, but it is good to understand the general structurings of your transformers, particularly because, I mean, looking through a couple of the past papers, there are a number of questions that Georgios asks that are very trivia based, they almost seem. So, welcome Georgios, let's do this. So, general analysis of transformers, we have the equivalent circuit. We can shift that to primary side or secondary side, ensuring that your turns ratio N is accounted for. Only in transformers, rather than in induction motors and such, are we allowed to pretty much make these approximate equivalent circuits, mainly because we are kind of saying that this whole core section is somewhat irrelevant because it makes up 2 to 3% of the actual current going through the system, so we sometimes ignore that for the sake of the relevance to our calculations. We have our open circuit test and short circuit tests in our transformers. These are really just, okay, let's get all the current to run through the core, and then, okay, let's get all the current to run through, well, pretty much all the current, all the relevant current to run through the windings. All right. Some bonus bits on transformers: step up, step down, auto transformers, potential transformers, and current transformers. Current transformer just being an ammeter, really. Yeah, there's not too many big things to cover in the realm of transformers, but we'll get into some of the nitty-gritty in one of the past papers. Past paper 2021 question 1G we'll cover. Just note, one of the little tricky things with 3-phase transformers is we can have 4 different types of topologies. We have delta Y, delta delta, Y delta, and YY. All this really does is, all that I will recommend that you consider for these is what it is that you're linking together. So if I'm linking together line voltages, then fantastic. Line to line stays the same. It's just NVN. Likewise, when I'm comparing deltas and Ys. All right. I believe mini mistake we made. Delta, delta, Y to Y. Opposite way around. Whoops. All right. Something to note, if we are converting delta to Y, we know that the voltages are going to convert because now instead of taking one voltage here to here, we need to take the summation of the two, so it's similar to our phase to line convergence. All right, so without further ado, here is the question. So this one was a 5-mark question from the 2021 final exam. One of the main, considerations for this, just a bit of context, I think this was it was one of the more mark questions for the transformer section. Typically, small trivia questions are like 3 marks. The larger trivia questions, which have words like explain and such, 5 marks. Sometimes you might get a really mean question that is like 4 different 3-mark questions, as we might see later in the crash course. So let's get into it. Transformers have a rated voltage for the primary and secondary windings. What conditions or design characteristics define these voltage ratings? Based on lab experiments, what impact does the use of a higher voltage than our rated have on the operation of the transformer? So there's a couple things they want us to do here. There's a couple things. Yes, we understand that there's a rated voltage for the primary and secondary. First notes on, the conditions on them is, okay, rated secondary equals, rated primary to secondary comes from our turns ratio. So, with that in mind, that is our first condition, turns ratio. Other things we need to consider for our conditions will be the maximum voltage rating for the transformer. Obviously, if we just shove way too much voltage, probably going to break something. But probably the biggest thing they want us to consider is based on lab experiments. When we pushed voltages through a transformer that were greater than rated values, we saw that there was a magnetization current that pretty much spiked, right? So big point is magnetization of the core. That is one of our big design characteristics for rated voltages. We want our rated voltage to be somewhat in a linear region, but when we push it higher than that, we end up with a saturation of the core magnetization. Saturation, when we look at the specifics of the impact of it, typically when we have our current waves, so I'll just call this current, we need to have an associated flux that comes with it. That is just our Lenz and just our EM laws. Usually we want some kind of linear relation to it. So what actually happens when we push in too great a current, so I'll say that these top bits get shoved, we see these spikes on our flux. And the reason is because the flux to current graph, it is something of an exponential. Sorry, not exponential, what am I saying? Something of a tan inverse graph. So, am I doing this the right way around? I to flux. Yeah. So there's a certain region in which we say, okay, it's not saturated, therefore somewhat linear relation, but as soon as we supply too much current, we see a massive jump in our phi. and this relates to the third harmonic because it is typically just in the middles of our waveforms for our flux that gets that big spike. That's where the third harmonic comes into it. And yeah, that is transformers, some trivia questions, and topic 2. I'll hand over to Jackson, who will carry you guys through topics 4 and 5.
Cool. Thank you, Otto. Just give me a moment to set up and then we'll get started. All right, let's get started. Cool, so topic 4, the DC machine. The first of the machines that we learn. So first of all, how does a DC machine work? Going back to HC physics, hopefully you guys have seen this before. The basic principle behind a DC machine is when you have a current carrying wire going through some permanent magnetic field, we can use right-hand rule to figure out the torques that are generated on this coil. So thinking of this one coil armature, if we have a current going this way, I'll do it in red. So if we have a current going this way and a field going this way, then we're going to have a torque generated upwards on this side and a torque generated downwards on the other side because we have a current going in the opposite direction. So that initially will create a torque that creates a clockwise rotation. But the issue is once we rotate 180 degrees, our currents will now be flowing in the opposite directions and we'll get a torque in the other way. So what that means is with this current setup that we have, just applying a DC current, there's going to be an oscillatory behavior because we're going to have a torque that pushes us clockwise, then anti-clockwise, clockwise, anti-clockwise, and we'll eventually reach standstill. So that's the principle. We're going to use that effect in unison with what we call commutators and brushes. So commutators and brushes are a mechanical rectifier for our signal or for our current. And what that does is every 180 degrees that we rotate, our current direction will flip. And that will ensure that our torque direction always remains in the same direction as we rotate around. So we'll have a torque that's always in the positive region. So if we look at it in terms of current, before our commutators and brushes, we had an AC current being generated, which causes torque to flip back and forth. But with the brushes and the commutators, we have a DC current, which is always in one direction. Just a bit on the construction of a DC machine. We have the stator, which is either going to be a permanent magnet or an electromagnet, and we'll see the difference in that when we look at the equivalent circuits. And then in terms of the rotor, that is your armature, and that is made up of your windings. Cool. So armature windings. Each DC machine will have 1, 2, maybe 3 windings in total, and each of those windings is made up of coils. Each of these coils being represented here. Each of these coils is made up of turns, and these coils are connected together end to end to create an entire winding. So if we wanted to know the total number of conductors that are in a DC machine, we would need to know the number of coils we have, the number of turns in every coil, and we would need to multiply that by 2. The reason we're multiplying by 2 is because if we look at the diagram, for one coil or for one turn, we have two sides of the DC machine being affected by the magnetic field. So we have two lots of torque being generated for every turn that we have. So that is why we have the 2 out the front. So simplex and multiplex, that's just terminology we use for describing how many windings we have in a DC machine. Simplex means 1, multiplex would be multiple. So for example, duplex is 2 windings. A new concept that we encounter going into machines is the concept of electrical angle versus mechanical angle. And that's because in a machine, we typically have more than one pole pair. So if you think of a mechanical rotation of 360 degrees that goes all the way around, sure, we have one full circular rotation mechanically, but electrically, a lot more is going on. Because if you think about it in terms of the poles, one full rotation is from one north pole to a south pole and to a north pole. So electrically, 360 degrees mechanical rotation is actually 120 degrees because we get that full electrical cycle happening in only 1/3 of the mechanical rotation. So that's given by our formula. Electrical angle equals the number of poles over 2 times the mechanical angle. All right. So moving on to something that Georgios likes to put in the exams a lot is the difference between lap, wave, and frog leg windings. Who is comfortable with lap and wave windings? Yeah? All right. Okay. Personally, it took me a while to understand these. And I'll go through them in detail just to make sure we're all up to scratch on them. Just to go through the definitions initially. Lap windings is when each of our coils are connected to adjacent segments. So say I had each of my segments, A, B, C, D, E, then we would have a coil which connects to the next coil and another coil which connects to the next one and so on. Whereas with wave windings, the coils that are connected together are one pitch apart. So we could have a coil that starts here, wraps around this pole, and then it would connect to a coil that is one pitch apart. And one pitch is from one north pole to one south pole. That's the distance of one pitch. So we'll get into the diagrams and how that looks. To go through a question, can anyone tell if this is a lap or a wave winding just by looking at it? Lap? Yeah, why is it lap? Okay, yeah.
But I think because it's not like it goes back on itself, it's not continuous.
Okay, let's go through it. So, as I said, with wave windings, or with lap windings, we have adjacent segments being connected together by just one coil. So what I like to do with these sorts of questions is I'll start at one segment. So for example, starting at segment A. At segment A, there's two parallel paths. We have one going to coil 1 and one going to the end of coil 8. So let's just follow it this way. So we have segment A connects to coil 1. Then coil 1 will loop around multiple times. And then, so like if I was going to show it through a diagram, each of these is a coil here. So this could be our first coil. One end is denoted by 1, and the other end of this coil is denoted by 1 dash. And then each of these coils will be connected together. So if we have 2 over here, then these will be connected by a wire, 2-3, these will be connected by a wire. And that's how we create lap windings. So the diagram might look a bit complicated, and that's because we're doing something three-dimensional on paper. So what we have is one end of the winding, and then we're going to loop around, and the other end of the winding is 1 dash. And this other end of the coil connects to coil B. So what I've had is starting at coil A, I've gone through a coil and I've hit segment B. So these segments are right next to each other. If I follow it around again, from B, I go to coil 2. The end of coil 2 then connects through to coil C, right? So we have another connection. How did I do that? We have another connection like this, and that connects to coil C. And this will continue all the way around. So we have each segment connecting to one another through adjacent coils. So this is lap windings. All right. This one here is wave wound. And the way that we realize this is by doing the same process. So let's start at coil A, at segment A, and let's go over to coil 1. The other end of coil 1 is over here, which connects over to F. So what we see, if we look at the diagram, we have A connecting through a singular coil to coil F. And these are very much not adjacent segments, right? The other thing to note is this isn't just some random connection from one segment to one segment. These segments are one coil pitch apart, as we mentioned earlier. So if we look at the diagram that we have 4 poles, which means that each pitch from north to south will be 90 degrees. So that is seen by the connection of the coil, which is one end at 1 and 1 dash. These are 90 degrees apart. So that's another way of identifying wave windings to lap windings. I have one more diagram to go through. So if we start again at A, and go through to coil 1, the other end of coil 1 is here and connects to coil B. So would this be a lap or a wave winding? Lap, yeah, because we've gone from A to B. One last thing I'd like to mention with lap and wave windings is that because of the way that lap windings work, and we need to have the same number of parallel paths to poles, when we look at these brushes that we have in our diagram, we actually need to have the same number of brushes as we have poles. So if we look at our lap, we have 2 positive terminals for our brushes and 2 negative terminals for our brushes. Whereas with wave, we only have 1 positive terminal and 1 negative terminal. And what that means is with wave, if you look at the segment that it's connected to, there is 1 path this way and 1 path this way. And we can follow these paths around to get to the negative terminal in 2 different ways. So that's 2 parallel paths. But with lap, because we have 2 pairs of brushes, sure, we can start at 1 segment and we again have 2 different paths to go down, but we also have 2 different paths from our other positive terminal. So in total, we have 4 parallel paths, which will reach our negative terminal in 4 different ways. So that is why with wave windings, we have 2 parallel paths, and with lap windings, we have as many parallel paths as we have poles. Cool. I'll get back to this question in a bit. Cool. So excitation, voltage, and torque equations. These are probably the most important equations in this whole topic. Your induced EMF equals some mechanical constant times your flux times your speed. Torque is the same constant times your flux times your armature current. And these constants are given by this formula. Z being the number of conductors that you have, P being the poles, and A, very importantly, being the number of parallel paths. So let's try apply that to the equation, or the question that we have above. So we have an 8-pole lap wound armature with 1,200 conductors and a flux per pole of 0.03 Webers. Determine the EMF generated when running at 500 RPM and calculate the EMF again if the armature was wave wound instead. So I'm going to use the equation that we just went through, which is E equals KE phi omega m. KE was Z P on 2A pi. So we have 8 poles and we are lap wound. So how many parallel paths would we have in this DC machine? 8, yeah, because we have the same number of poles as we have parallel paths. So A is 8. Z is given to us. Z is 1,200. And P, the number of poles, is 8 as well. So we can calculate KE to be 1,200 times by 8 over 2 pi times by 8. We can sub that into the equation to give E equals 1,200 times 8 over 2 pi times 8. Our flux per pole is given as 0.03. And our speed given in RPM is 500. We can't leave it as RPM. We need to convert it to radians per second. To convert to radians per second, we just simply multiply our RPM by 2 pi on 60. So if I simplify this, these two will cancel out. This will be a 20. This will be gone. And then we have 20. Oh, we have the 8s cancel out as well. We have 20 times 500 times 0.03. And that will be 10,000 times 0.03, which gives us 300 volts. Cool. So this is for lap wound. So if we repeated the same question for wave wound, the only difference would be, rather than having 8 parallel paths, we would have 2 parallel paths. So for wave wound, we would get the same thing. So it would be the lap, but rather than dividing by 8, we're dividing by 2. So our EMF will be 4 times greater. So this will be 1,200 volts. So this brings us to an important conclusion, which is that when you have wave wound, you can get a lot more voltage out of the same machine essentially by just connecting the coils in a different way. So in practice, what we find is that with lap wound, we prefer to use lap wound for high current, low voltage situations, and we prefer to use wave wound for high voltage, low current situations. And that can also be explained by the number of parallel paths that we have. So with wave wound, you might have 2 parallel paths, which allows some amount of current through each. But with, so that's wave wound. But with lap wound, you can have many more parallel paths, which means you're allowing a lot more current through. So that makes it more applicable to high current. Does that make sense to everyone? Wave and lap? Okay. Because yeah, that's come up in almost every final exam. So yeah. Moving on to magnetization curve of DC machines. We have primarily linear behavior between your flux and your MMF. But what happens is, because we're dealing with cores, we're going to have some point of saturation, as we've seen in transformers. And then moving on to our equivalent circuits. Our first circuit that we look at is a separately excited DC machine. Its main feature being in the name, it's separately excited. So this would describe some sort of circuit where you have an electromagnet or a permanent magnet that's powered by an independent DC source. So the EMF that's generated is completely independent of your armature voltage. I won't go in detail through the equations because the equations are just simple KVL, KCL, Ohm's law from Quad 1, which can be derived in when we go through examples as well. One important thing to mention is that the direction of current will change whether we're looking at a generator or a motor. For a generator, we have current coming from our induced voltage source and going out to our terminals to power some load. Whereas with the motor, we have our supply terminals moving current towards our induced voltage. All right, shunt excited and series excited. Again, it's in the name. So shunt means that our field excitation is in parallel with our terminal voltages, or in parallel with our armature. And what that means is we're using the same voltage source to both create the magnet that's going to turn the rotor, and we're also using that voltage source to supply power to the rotor as well. With series, very similar. We're using the same voltage source to power both, but the difference now is that this excitation is in series, and we'll get to more on with the differences in the behavior later on. Short compound versus long compound. Again, it's in the name. So compound means that we are adding together the impact of 2 different excitations. So we have the shunt excitation and the series excitation. The difference between short and long is simply in where we place that shunt branch. So in short, we have an armature with a shorter electrical length or less components, and in the long, we have an armature that has more electrical components connected. So that's where the name comes from. One important thing I'd like to mention is there's 2 types of compound. You can either have your fluxes from each excitation adding together and working together, which is our cumulative, or you can have them working against each other, which is differential. Differentials in general, just a bad idea. It creates instability, and it's also quite a waste of power because you have two excitations that are working against each other, which just doesn't make sense, really. Cool. So let's jump into a question. The current in the armature of a shunt generator is 120 amps when the terminal voltage is 440 volts and the speed is 800 RPM. The armature circuit resistance is 0.2 ohms. Calculate the new speed when the armature current is reduced to 60% of the initial value and an additional resistance of 1.5 ohms is connected to our armature. We're assuming that the field strength stays the same. So the first thing I'd like to note is we're dealing with a shunt generator. So if I draw the circuit, we have our armature resistance and our shunt resistance, which is also our field. I've left out the inductor in the circuit, and the inductor can be left out because one, we're dealing with DC machines, so this will be steady state, and the inductor itself is sort of like a fictitious inductor, and it just represents that that branch is responsible for generating our induced voltage. So we don't actually have to include it in our calculations. All right, what else are we told? We're told that 120 amps is flowing through the armature. So since it's a generator, we have 120 amps flowing from our EMF source to our load. So this will be our load current. And we also have some finite armature, we have some finite field current as well. Okay. We are told that the terminal voltage for the generator is 440 volts. And we know that the speed is 800 RPM. So somehow I need to use an equation that we've covered to first look at how an EMF generates a speed, and then we're going to look at how that change in EMF will create a change in speed. And the equation I'm going to use to describe this is our trusty E equals K E phi omega m. So we know phi, or we don't know phi, we know K E phi is going to be constant, and we are given omega m being 800 RPM. But we need to find E. How could I find E from the circuit that we have? So how could I find the voltage at this node? Sorry? Yeah. Close. It'll be plus because we're gonna have it's a generator. Yeah. Great. Thanks. So we're gonna have VT plus IARA is our EMF. So this is 440 plus 120 times, and our armature resistance was 0.2. So this gives us a value of 464 volts. So then I'm going to analyze the new circuit. So what's changed is we have our armature current reduced by 60%, and we've increased our armature resistance by 1.5 ohms. So now our armature current, so this is our new circuit. We have our armature current is going to be 60% of 120, which is 72 amps. And our new RA is 1.5 plus 0.2, which is 1.7 ohms. So I can use the exact same formula to find EA again. EA will be VT plus IARA, which gives us 440 plus 72 times 1.7. And this gives us a value of 562.4 volts. So I have the original EMF generated and I have the new EMF generated. So now I'm going to use this equation to compare how the speed will change. So if I have the old EMF is proportional to the old speed, and the new EMF is proportional to the new speed, I can create a ratio. So I will know that the old speed over the new, or the old EMF over the new EMF is the same as the old speed over the new speed. And just subbing in these values that we have, we can arrange for omega n. Omega nu will be 562.4 over 464 times 800. And that gives us a speed of 969.6 RPM. Great. Any questions about that example? Right. Cool. I'll move on. So going back to commutation, with commutation previously, we assumed that it was ideal. And that means that when we flip our armature 180 degrees exactly, we assume that the current direction will flip immediately. And what we realize in reality is that that is definitely not true. And that is because our coils themselves act as inductors. And if we remember what inductors do to current, they oppose a change in current, which means that we can't have this instantaneous change. So if I look at this diagram, this is what we would expect in the ideal case. We would expect as our brush moves between segments, the current will change proportionally. So here we would have a quarter of the current through armature A and 3/4 through B, half, 3/4, 1/4. And then ideally we would expect as soon as we flick over to that new segment, all of our current is already through the segment A. But because our coils act as inductors, we have a delay in our current changing. So once we've swapped over entirely to segment A, we might not have all the current through A, and we might still have current trying to flow through B. And what that causes is an induced voltage, which will create arcs here. And those arcs will create sparking, which is another form of loss that we have in our circuits. So yeah, that's what I've said in the bottom left. The efficiency of DC machines, typical efficiency equation, and we have each of these losses. So this is your armature resistance loss, your field resistance loss, and then any frictional losses through your brushes, and these will be constant losses. So we've seen them here as well. So our mechanical losses and core losses are constant, so it doesn't depend on the EMF or the speed of the motor. And we'll see that in an example of how we account for that and then get a final answer for our total losses. Just more on typical losses. Electrically, we have the copper loss or the I²R loss in the field and the armature, plus any brush contact losses like voltage drops across the brushes and sparking. Mechanically, we have friction losses, and magnetically, similar to transformers, we have hysteresis and eddy current losses. Torque and speed characteristics. Some definitions on the top left. Starting torque is a torque at speed 0. Pull-up torque is the minimum torque generated between our entire range of speeds. Breakdown torque is the greatest torque we achieve, and full load torque is the torque at our rated speed. Speed regulation is given by this equation. And yeah, let's jump into the behaviors of each motor. So starting with the shunt motor. The great thing about the shunt motor is that the speed of the motor doesn't really depend on the current. And since torque is proportional to current, that means the speed of the motor doesn't really change depending on our load, which is fantastic in certain circumstances. The one issue with this is that with other setups, we could be getting a lot higher starting torque than what we have with shunt motors. With series motors, we instead have the torque is proportional to the current of the armature squared. And our speed versus torque graph looks very, very different. So we have very high speeds at low torques and very high torques at low speeds. And that's great for when we have to move a very large load from like standstill. But again, there is a downside, which is that you can see that our speed varies massively with the torque of the machine. So our speed is not regulated very well, and it will depend very largely on our load. So lastly, compound. If we remember compound, it's when we have a combination of shunt excitation and series excitation. And the benefit of this is that we get the best of both worlds. So with the shunt characteristic, we have relatively constant speed across different torques, if we look here. And with the starting torque, at low speeds, we have a pretty high torque as well, which was a consequence of, which was a downside of shunt motors. So with compound, we get the best of both worlds. Just to comment again, differential, looking at these three graphs, is worse than a shunt motor in every single way. So we don't use differential. Cumulative is the way to go. All right, let's jump into another question. A 400 volt DC shunt motor runs at 1000 RPM and takes an input of 1500 watts under no load. The armature and field resistances are 0.3 and 200 ohms respectively. Find the efficiency when the machine is used as a generator, supplying 100 amps and 400 volts. So I'm going to use the first two sentences to find the losses for our no load condition, and then I'm going to use those values again when we're going to be looking at the machine in a generator setup. So let's start with this shunt motor. So we have 0.3 across the armature, 200 across the field. And we know that we have 400 volts at our terminal. And we're running at 1000 RPM. The other thing we know is that P in is 1500 watts. Great. So using the information that we have, we know that our input power will be our input voltage times our input current. So that's simply 400 times your input current. And we know that the input power was 1500. So our input current is 1500 over 400, which is 3.75. So in our motor setup, we have 3.75 amps here. And we want to find the current IA, so we can find EA. The way we're going to do that is we're going to find IF first. So using Ohm's law, we have 400 volts across a 200 resistor. So we have IF is 400 volts over the resistance, which is 200. So we have 2 amps flowing through our field. So then IA will be whatever's left of our current. So 3.75 minus 2 amps, which is 1.75. Great. So now we can calculate all the losses in this circuit. So our loss from our RA will be IA squared RA, and our loss from our field resistance will be IF squared RF. So if we sub in the values, we get 0.918 watts loss for the armature and a much larger 800 watts loss for our field resistance. So what we notice is that even though we're supplying 1500 watts, we're only getting about 801 watts losses in our circuit. And because we have no load, the other losses must be coming from some other point in our circuit, which is represented by the loss across our induced voltage. And these losses represent our constant losses. So they represent the friction and the hysteresis and eddy current losses. So I need to find that so that I can use that in our next example. So we need to find constant losses is going to be our input power minus field losses and minus armature losses. And this gives us 699.0, roughly 02 watts. So this loss is constant, so it's not going to change when we look at the generator under different conditions. Now let's look at the generator. So with the generator, we are supplying 100 amps. My bad. The generator will have current going from our induced voltage to our load. And from the load, we are receiving 100 amps. And we have a terminal voltage of 400 volts. So if we look at output power first, that would just be output voltage times output current, which is 40 kilowatts. So next, again, we're going to find the losses across each of the resistances and add on the constant loss that we have, and then we will be able to find the efficiency. So we know that the input So we know our input power is going to be the total of all the powers in our circuit. So if input power is going to be output power plus the loss across RA plus the loss across RF plus our constant losses that we have. So this will be 40k. Now to find RA and RF, we need to find the currents again. Using Ohm's law again, we know that IF will just be 2 amps, 400 over 200 again. And we know that the armature current will have to be the sum of 100 and 2. So it will be 102 amps. So I can use this in our calculation. 102 amps squared times 0.3 plus 2 amps squared times 200 plus our constant losses, which was 699.02. And what we find is the total input power is going to be 44,620.3 watts. So last thing, we can find the efficiency. Okay. We can find the efficiency by going output power over input power, which is 40k over 4,400,620.3, which gives us an efficiency of 0.8965. Cool. So yeah, the important takeaway is we're using one set of conditions to find the constant losses, and then we're using that to find the efficiency when we have a different setup. Last thing on topic 4 is starters. So you can imagine when we're starting a motor, it's at standstill, which means that there is no change in flux, which means that we have no current flowing through. If we have no current, then we have no, sorry, that is not correct. If we have no change in flux, we have no EMF being produced. And if we look at our circuit, if this is 0, then all of our voltage drop will have to be across this resistor. So this current will be at a maximum because we have a maximum voltage drop across this resistance, which is still the same. So when we're starting a DC motor, what we find is that we're going to have the largest current that this motor will ever experience. And that can be an issue with, for example, supplying too much current to our motor and causing damage. So we've come up with a couple solutions for starters, which is just adding on certain amounts of starting resistors to reduce the current at starting, and then we can eventually reduce that resistance so that we're at full operation. Cool. So that's all of topic 4. Does anyone have any questions? No, all good. All right, topic 5, the induction machine. So induction machines work very differently. The main difference is that instead of supplying DC power, we're supplying 3 volt AC. And the way this works is that we're having 3 different voltage sources, 120 degrees out of phase, which will cause a rotation of our magnetic field in our stator. And that rotating magnetic field will create a changing flux, and that changing flux will induce an EMF in our rotor. Then the induced EMF in our rotor will generate its own magnetic field through Lenz's law, and the interaction of those 2 magnetic fields will create a torque or a rotation on our rotor. Yep. So one thing to note, this is the general setup. We have armature windings through our rotor, which is, if we think of it analogous to a transformer, that's our secondary windings. And then we have windings in our stator, which is like our primary windings in our transformer. So we're generating an EMF, which generates a change in torque. So a bit on the construction. We have the stator, which is made up of our windings, our core, our frame. And then more interestingly, our rotor can be made in 2 different ways. The squirrel cage rotor is great for being robust and cheap. The issue is that you can't really make any changes to the circuit because we don't have access to the 3 windings themselves. With the wound rotor instead, it's less robust, but we have access to the 3 windings, which means that we can add resistances, and we'll see why that comes in handy when we're looking at torque characteristics. So in induction motors, we're introduced to a concept called rotor slip, and that is essentially because with an induction motor, we don't want to be operating at the synchronous speed. You can imagine if we're operating at the synchronous speed, the rotor is moving at the exact same frequency as the stator, which means that from the rotor's perspective, there's no change in flux. And that means that without a change in flux, 1, we're going to have no induced EMF, and 2, we're going to have no torque produced, so the motor can't actually do any work. The synchronous speed is a new terminology, which is simply the speed of the rotating magnetic field, and we use that to calculate slip. So slip is just the synchronous speed minus the motor speed over the synchronous speed. One thing to note is this is like a actual value divided by a base value, so slip is actually a per unit value. At standstill, our motor will be 0 speed, which means that we will have our maximum slip of 1. And when our motor speed is equal to the synchronous speed, we're having a slip of 0, which translates to a torque of 0. One very important thing to do with the behavior of an induction motor is that from the rotor's perspective, since it's also rotating at some speed, slightly slower than the rotating field itself, it actually sees a change in frequency that's a lot slower than from our perspective from outside the induction motor. So even though the synchronous speed creates a frequency of the stator rotating at, say, 50 hertz, our rotating rotor, will see a slower frequency. And that means that we have to express it in our equivalent circuit as 2 isolated circuits connected by a transformer. And that becomes really tedious when we want to do analysis. So the workaround for this is we take our current and we divide everything by S such that the current remains the same. And instead of having our EMF and our reactance being multiplied by S, now we're dividing by S for our resistance. Next, we're going to split this resistance into a constant resistance. This represents rotor losses. And this resistance here, which is dependent on slip. This represents whatever mechanical load we have attached, which will be causing that change in slip or change in velocity of our two, of our rotor and our stator. So with those changes, we're able to create this simplified circuit. So the main thing to notice is that our transformer's gone, which is great. And another thing to notice is that we've neglected RC. Reason for that is that RC is generally very big. So one, we can neglect it. The other thing is that if we do account for it, we account for it in our constant losses because it's approximately constant. And we'll see that later on. Similar transformers, we have tests to figure out the parameters of our induction motor. So measuring R1, we do that by simply turning off the motor, leaving it at standstill, and we measure the resistance between two terminals. This will change depending on whether we have a star connected induction machine or a delta connected induction machine. So if we look at our resistance that we measure between these two terminals, this is two resistances in series. So this is simply going to be twice of R1. If we're in delta, if we look at the resistance between these two terminals, we have one resistor here in parallel with the sum of these two resistors. So R1 parallel to R1, which is 2 on 3 R1. Next we have our no load test and our blocked rotor test, which we use to figure out all the other parameters in our circuit. So no load obviously means we don't have a load attached, which means that our secondary terminals will be open circuited, or our rotor terminals. And that would mean that roughly we have a speed which is close to the synchronous speed, which consequently means that our slip is 0. So then we can use these simplified equations to find values for our no load impedances. Blocked rotor test, similarly, instead of having an open circuit at our rotor, we're shorting it, and that creates very large current, and we have very little voltage across our XM, which creates a simplified circuit. And again, we use these parameters to solve for our, we use these equations to solve for our parameters. Power relations. So there are a lot of losses that happen in an induction motor. From our input power, we have losses from our stator resistance and our stator reactance, which is represented by I squared R. Our core losses are, like I said earlier, RC we typically neglect, but it is there. And then we have our power transferred across our air gap, which is P in subtracted by these two losses. And then we have again more I squared R losses from our winding in our rotor. And then we have mechanical power being outputted. And then lastly, we have our constant rotational losses, which is our windage and our friction losses. And at the end, we get some output power. These are all the equations. I will be using some of them in the example that we're about to do. All right. The following test results were obtained from a 3-phase, 75 kilowatt, 415 volts, 8-pole, 50 hertz, Y-connected squirrel cage induction rotor. The no-load test gave these parameter values, blocked rotor test gave these values, and we're given the DC resistance between any two terminals is 0.06 ohms. So question A, determine the parameters of the rotor, and we're simply just going to be using all these values that are given. All right. So the first thing I'm going to do, I'll start off with what's easiest, and that is the DC resistance test that we're given. So we know that, importantly, it's Y-connected. So if we think about our resistances measured between two terminals, this is simply going to be twice R1. So since we measured 0.16, our R1 will be 0.16 divided by 2. So this would be 0.08 ohms. Next, we'll look at our our no-load test. So if I look up at the no-load test, first I'm going to use this equation to find R no-load, this to find Z no-load, and then I'm going to use Pythagoras to find X no-load. So let's start with R no-load. So R no-load is going to be the power over over 3I no load squared. So this is 4k over 3 times 40 squared. And this gives us a value of 0.8333 ohms. Next, I'm going to find Z no load, which is simply the magnitudes of the voltage and the current. So that is 415. Importantly, this is star connected. Remember that we're always given line voltages. So when we do calculations, these all need to be phase. So this needs to be divided by √3. And our current, phase current, is equal to line current in a star connected setup. So we have 40 amps. And this gives us a value of 5.99 ohms. So then we can find X no load, which is Z minus R, and that gives us a value of 5.932 ohms. Cool. So if we remember our setup from before, for our no load test, our X is a representation of this impedance, X1, in series with this impedance, XM. So what we calculated here is actually X1 plus XM. So that's all for our no load. Now we're going to use our blocked rotor test. With blocked rotor, we can apply the same formula to find block rotor resistance. And this is going to be this resistance in series with this resistance. So we have RBL equals PBL over 3 I squared BL. So we have 8.1K over 3 times 130 squared. And that gives a value of 0.1598. And that is R1 plus R2 dash. So we already know R1. So now we can finally get an actual parameter out of this. R2 dash is our blocked rotor resistance minus R1. So that's 0.1598 minus 0.08. So this is 0.0798 ohms. Great. Next we can do the blocked rotor impedance. Again, this is voltage over current. Voltage needs to be in phase, so we're going to do 100 divided by √3. And our current is going to be 130. So this gives us a value of 0.444. And again, we can use R and Z to find X. And this gives us a value of 0.414. Cool. So we're actually not given enough information in this question to find X1 and X2 dash themselves. So usually a safe assumption to make is that, we also did it in our labs, is that X1 is approximately equal to X2 dash. So since this is the sum of those two, we're going to assume that these are roughly equivalent. So then XBL will just be half of that for both. So we have X1 equals X2 dash equals 0.207 ohms. So we found X1, X2 dash, R2 dash, R1. The last thing to find is XM. So XM we know is X no load minus X1. And now from our blocked rotor test, we actually know what X1 is. So this is the last thing. We can do no load which is 5.932 minus x1, which is 0.207, and that gives us a value of 5.725 ohms. Great. So that is all of it. Part B. The same induction motor is now connected to a three-phase 415 volt 50 hertz supply, runs at 725 RPM. Determine the input current, input power factor, like basically all the powers. We're going to find all of the powers, which is annoying, but anyway, here we go. So we have our circuit. And from the last part, we know all the values. So we have R1, X1, XM, R2 dash, X2 dash, R2 dash, 1 minus S over S. Actually, we might not have enough space here, so I will move this over. I guess I'll do it up here. Cool. So this is V1. From our question, we know V1 is 415 on route 3. And we know that our supply is 50 hertz and it runs at 725 RPM. So I'll just note that all down up here. So V1 is 415 volts on route 3. And our omega M is 725 RPM. Did I miss anything else? 50 hertz supply, but we typically assume that anyway. So first thing to do is we need to find input power. So to find input power, we need to find input current. So P in is going to be, because we're in three phase here, we need to do root 3. Actually, we're dealing with phase, so let's do it in phase. So we have 3 V phase, I phase, cos theta. So we need to find I in. So I in will be all of the resistance of this circuit, or all of the impedance of this circuit, over the voltage. So we have V1 over. So I'm going to make this all parallel. So this is XM parallel R2 dash plus X2 dash 1 minus S over S. These resistances, when you add them together, these become R2 dash over S. So we have R2 dash over S plus X2 dash. And then we're adding that in series with this. So this is X1 and R1. Don't forget the J's. So as I can see in here, I need slip to actually get this value. So we're going to find slip to start. So to find the slip of this one, we know that the synchronous speed is going to be 120 F over P. So this is 120 times 50. I missed it earlier, but it did say 8 pole. And this will be 750 RPM. So to find our slip, then we do synchronous minus motor over synchronous, which will be 750 minus 725, which is 25 over 750, which is 1 over 30. Cool. So I can chuck in all our values that we had earlier. So we had R1, R2 dash were both 0.08 roughly. We had X1 was X2 dash, which was 0.207, and we had xm was 5.725. So we're going to use all these values. Chuck them all in. I have the answer, so I'll just write it down. It's 103.05 with an angle of negative 30.62. The negative angle makes sense because in this case we're dealing with induction motors, and induction motors are always lagging. So we have P in is 3 times 415 on root 3 times 103.05, and our angle will be voltage angle minus current angle, and this is simply 0 minus negative 30.62. So this is 30.62. So we get a value of 63.74 kilowatts. So that's the first step. It also asks for power factor. Power factor is simply cos of the angle that we have, and that will be 0.861 lagging. Next, we are asked for the air gap power. It might be good to look through this diagram. So we found P in, and now we want to find the air gap power. So to find air gap power, we need these two losses, and we need to subtract them from P in. I lied. We're not going to find this because this is negligible, and this will be accounted for in our constant losses. So first, let's find I squared R. So we know that P air gap will be P in minus our losses across our stator. So we have 63.74K minus the loss across these resistance, this resistance here. So this will just be I n squared times R1. So we have 103.05 squared times 3 because we're in 3 phase, and we're timesing that by R1, which was 0.08. So our air gap losses in total will be 61.195 kilowatt. Next, to find the losses in the rotor resistance, I'm just going to use the formula that we're given. So rotor copper losses is S times the air gap power. We know S and we know the air gap power. And I'm also going to find the developed power while we're at it, which is 1 minus S times the air gap power. So let's do that. So P losses in the rotor is going to be S, which was 1 over 30 times the air gap power, which gives us 2.0398 kilowatt. And the power we get out of that is 1 minus 1 over 30 air gap, which gives us 59.155 kilowatt. Cool. So now we're at this point. The last step is to find the constant rotational losses. And to do that, we're going to use this formula. So this comes from our no load test, which we had in part A. So we have 3 times the no load power minus no load current times R1. So the constant losses is 3 times the no load power, which was 4K, I believe. Yep, it was 4K minus, my bad. So this is already 3 phase, so I'll divide that by 3. So these 3's will actually cancel out. So we have 3 phase power minus 3 times no load current squared, which was 40, times our R1, which was 0.08. So our constant losses come to a value of 3.616 kilowatt. Alright, going back to our diagram, the output power is simply P in minus the constant losses. So the output power is PE minus P constant. So that gives us a final value of 55.54 kilowatt. Okay. So yeah, that is that question. Does anyone have any insights or inquiries? It's a lot of bash, but yeah. This diagram is very helpful. Personally, I'm going to put it on my cheat sheet, just in case a question like this comes up. Cool, we'll move on. All right, torque. So, with torque, we are looking primarily at the torque generated by the rotor. So that becomes very annoying because our circuit has a branch in the middle. And we're going to be doing a lot of torque calculations usually. So to make it simpler for ourselves, what we usually do is we create a Thevenin equivalent of that circuit. So looking through the terminals here, we're going to look at the Thevenin equivalent resistance and voltage to create a new circuit that we see here. And that is given by these two equations. After we've done that, we can apply all these nice formulas. So the torque is given by this massive equation, which would be if we're looking at the simplified circuit. If we're looking at our original circuit with the branch through it, we can use this circuit here, this equation here. Starting torque, we know that at starting, our slip will be 1. So this is just this equation simplified with all the slips being 1. And we can see that there in the starting torque equation. Maximum torque, which is the point here, that will occur when we have maximum power transfer. We have maximum power transfer when the impedance of our stator is equivalent to the impedance of our rotor. And so by equating R2 dash R2 dash plus JX2 dash, this should be on S, R1 minus JX1, because we want the Thevenin to be equivalent to the load conjugate. If we rearrange that, we get this equation, which tells us where the maximum slip occurs. An important note here is that the slip is very dependent on our resistance on our rotor. And this is where wound rotors come in handy, because with wound rotors you can change the resistance of the stator, and thus you can change where your maximum torque happens. Next thing is this equation. So this equation shows that the torque maximum doesn't change even though we change the resistance of the rotor. We will still have the maximum torque at every point. So yeah, that's what I've explained here. As we can see in our maximum torque equation, this is independent of R2. And this one is very dependent on R2. Okay. Starting an induction motor. So the way an induction motor will starts at 0 speed, which gives us a slip of 1. So that means that our rotor resistance will be at a minimum, because that is R2 divided by S. That means that our current through our rotor is a maximum. So we have, again, the same issue where we have a lot of current going through our rotor at starting. So we've introduced two different ways. Well, there's more, but I've gone through the two main ways that we can account for this massive current. One way is changing the setup of the loads. So rather than being in a delta connection, we start in a Y connection, and that will reduce the total current. And then once we're in operation, we will switch to delta. In the auto transformer, what we're doing is we're essentially fixing the voltage to something lower while we're starting up so that we have less current going through. Modes of operation. So we have three primary modes of operation. What we've just gone through is these two modes here, motoring and generating. When we have a slip that's between 0 and 1, we're motoring. Generating is when we're supplying some extra mechanical power to make the rotor spin faster than the rotating magnetic field. And that will cause that mechanical power that's in excess to be converted into electrical power at our terminals. Braking mode is essentially when our rotor is spinning in the opposite direction of our rotating field. And that means that we would have a negative speed with respect to our rotating field, which causes the motor to slow down very rapidly. All right. How are we for time? Good? Okay. Let's go through another question then. Using the equivalent circuit parameters found in question 26, find the following for the induction motor when supplied with rated voltage and frequency. So this whole equation I can see is all about torque. So to make life easier for myself, I'm going to find the Thevenin equivalent first. So one thing to note is we're meant to be given a bunch of parameters. I have them written somewhere. Question 27. This one, yes. Okay, so I'll write all the parameters. So we were meant to be given R1 is 2.8, XM is 274.4, X1 is 6.63, X2 is 6.65, R2, 2. Okay, that should be everything we need for this question. So first, I'm going to draw my circuit. So we have, again, this setup. So to make life easier, I'm finding the Thevenin equivalent into this terminal here. So when I'm looking at my voltage from my V1, I have a voltage here, Vm, which is simply going to be a voltage division between each of these impedances. So we have Vm will be JXM over JXM plus R1 plus JX1. So that's our voltage division there. If I sub in all of the values, I will get 1240.3 volts. Next, I can find the equivalent impedance. So to find equivalent impedance, I'm going to short my terminal here because we need to turn off voltage sources for a Thevenin equivalent. And then we're going to find that the impedance looking from these terminals will just be XM in parallel with R1 and X1. So we have ZTH is XM parallel with R1 and JX1. Again, if we sub in all the values, we will get a value of 2.67 plus J 6.5. Alright, so I can redraw my circuit. We have VTH, RTH, XTH, cool. So this is what we have. R2 dash X2 dash R2 dash 1 minus S over S. Great. So to find starting torque, I'm going to apply the equation for starting torque. So we have everything we need actually. So starting torque is going to be 3 times R2 dash, which is 2, times VTH squared, which is 1240.3 squared, all over the synchronous speed. The synchronous speed is given as 1000 RPM. Again, we need to make sure this is in radians per second, so 2 pi on 60. And then we're going to multiply that by, that will be RTH plus XTH squared plus And that is R1. No, wait, my bad. Because we're summing imaginary with real, we need to sum all of the resistances together and then take that absolute value. So this will be RTH plus R. So this will be R2 dash. Because looking at our circuit, we have two resistances, which is RTH and R2 dash. Looking at our inductance, we have XTH and X2 dash, and that will be squared. So subbing in again those parameters that we're given, we will get a final value of 452.63 Newton meters. Okay, so that's the first question. B, find the slip and speed at which maximum torque occurs. So again, using the equations that we have, maximum torque will occur at this slip. So we have R2 dash on the square root of RTH squared plus RTH plus XTH plus R2 dash squared. So we have S equals R2 dash, which is 2, over the square root of RTH squared. So RTH was 2.67 plus XTH 6.5 plus X2 dash 6.65 squared. And that gives us a value 0.149. If we look at our mode of operations, 0.149 is very close to here. The reason we have this full load, or the maximum torque, my bad, here. Actually, I'll explain that later once we draw our diagram. That's all right. Cool. So then we need to find the speed from this. So speed, omega. So we know S is omega S minus omega M on omega S. So we can rearrange this. 0.149 equals 1000 RPM minus motor speed over 1000. Rearrange this, we get omega M is 851 RPM. Cool. So we found the maximum slip and the speed at that slip. C, find the maximum torque that the motor can develop. So I won't go through it in detail. We're simply just going to use this equation to find the maximum torque. It's quite straightforward. If we apply the equation, we get a maximum torque of 1,371 Newton meters. You can double check that yourselves if you want to work through it in your own time. And then D, find the developed torque and speed at the rated slip of 0.1. So again, this is not a very exciting question. We're just going to be using the equation that we have here, which lets us find the torque for any slip value. So we're just going to sub in all the parameters with slip as 0.01. And we will get a final value. If we sub in those values at slip equals 0.01, we get a torque of 213.2 Newton meters. So you can try that again in your own time. E, draw the torque speed characteristic from what we found in A and D, A to D. So we know our torque speed characteristic will look something like this. This is our maximum torque, which was 1,371 Newton meters. We know that this is at our synchronous speed, which is 1,000 RPM. And we know our starting torque was 452.63. And we have at a slip of 0.01, we have a torque of 213.2 Newton meters. F. To make the starting torque equal to the maximum torque, how much additional rotor resistance is required? Alright, this one's a fun one. So if we look at our equation for maximum torque slip, we have this equation here. And if we want the maximum torque to occur at 0 speed, what slip do we want? What slip do we have at 0 speed? 1, yep. So we're trying to make this equation equal to 1. So it's asking how much more resistance do we need to add to our rotor to create this. So we have R2 dash on RTH squared plus XTH plus X2 dash squared. And we need to equate this to 1. This will not give us a value of 1. We need to be adding on some external resistance, which I'll denote here. And then we can sub in the values and equate. So we know that R2 dash is 2, RTH is 2.67, X2 dash is 6.65, XTH is 6.5. So I'll sub that all in. So we have 2 plus R extension over the square root of 2.67 squared plus 6.65 plus 6.5 squared equals 1. If I rearrange this, I will get a final value of 11.39 ohms. Cool. Alright. Does anyone have any questions about torque? Usually it's just using the equations that we have. Yeah. Okay, yeah, sure. Good question. So we're being asked how much additional rotor resistance, right? So we just add that on to our R2 dash. Last part. Sometimes we want to use induction motors that aren't three-phase. So to achieve this, we're using a single-phase power source, and we're using that to create 2 poles. And this creates an oscillation of our magnetic field. Rather than being rotating, our magnetic field is actually oscillating from side to side in magnitude. In principle, it would be cool if we got it working, but the issue is that we have 0 starting torque because there's no actual rotation. So the motor itself doesn't know what direction to follow, I guess, because it's just oscillating back and forth. So something we use to get this working is the double revolving field theory. And we can equate an oscillating field to a field that's moving in one direction and a field that's moving the other direction. So clockwise and anti-clockwise. So then we would have an MMF that's generated in the forward direction and an MMF that's generated in the backward direction. So in principle, if we can get the motor turning in one direction, then it will be able to follow one of these MMFs or one of these changes in flux, and it will continue rotating. So we get it starting, for example, using an induction motor, and then we have this interesting curve here, which is simply the sum of the forward EMF and the backward EMF characteristics. So the forward EMF characteristics summed with the backward EMF characteristics gives us our torque speed curve. So it's very similar to the past analysis that we've done, but because we have 2 different fields we're accounting for, we're having 2 different rotors in our equivalent circuit. And this gives us all these massive equations to work through. Yeah, hopefully Georgios isn't that mean. Fingers crossed. But yeah, if that does come up, that's how you do it. Cool. That ends topic 5. I'll pass on to Otto to cover topic 6.
Can we give Jackson a nice round of applause? Fantastic. Fantastic stuff. All right. There's my book. I just put it down. Let's get this rolling. So, topic 6, synchronous motors. Probably, I mean, it might be the section with the fewest slides in the lecture notes, only at 97, but oh my gosh, I love this course. All right, so synchronous machines. We began the topic with synchronous generators simply because that is I guess it has the fewest finicky bits in it initially. We rotate a DC field in the rotor, which is DC excited. That rotates and generates an AC oscillating fields in the stator. That's the general, I guess, operation. We pretty much flip up where the armature and rotor are. The stator is now the armature, and the rotor is now the field generator, which is fundamentally different from all of our previous, I guess, renditions of motors. And yeah, it is our doubly excited motor or generator. All right, there's not too much to chat about here. Rather generally, in terms of questions that are asked about the synchronous motors and generators, just synchronous machines, they're all to do with, okay, here's an equivalent circuit, let's throw a ton of equations at it, and yeah, there's not too much to yap about, but let's go ahead and consider a couple more things about just how a synchronous generator operates. So, one of the primary things is we need excitation of the DC field at the rotor. There are two ways that are described in the lectures, that being our brushed exciter and a brushless exciter. The use of a brushed exciter does have the negative of constant friction at the slip rings. We have our equivalent circuits. A special note is that Georgios was kind of hinting at this, and I'm a little scared he might include it. He includes 3 separate circuits for the stator, okay? So there is a lot of potential for each of these, I guess, stator windings to have different resistances and therefore potentially different calculations. So just something that we typically want to make sure we're accurately considering is we only use the per phase when we're considering balanced loads. Typically we will, but it is something that we might need to take special care about. All right. So we have 3 tests as opposed to 2 for our synchronous machines. So we have our DC resistance test. This is where we measure the armature resistance as per some DC excitation of the stator. So, I mean, it's a little strange, especially because, wait, where's the pen? You have the pen. It's a little strange just because we are now considering the armature in a DC fashion, where we were just told that it generates AC things. Essentially, by taking the current going through here at DC, the inductors, or equivalent inductors, are bypassed, and so we just get standard Ohm's law running through this resistor, which is fantastic. Note that while we might actually be working at higher frequencies, typically the change in frequency does not have a significant skin effect. It might have some minute skin effect, which is just, okay, AC resistance is a little different to DC resistance, but that is the concept. We're using DC tests to measure RA. Note that we're using, it's a measurement, and it's between 2 terminals, so depending on whether you're Y connected or you're delta connected in your synchronous machine, you have the exact stuff from topic 5. Right? Fantastic stuff. Next up, we have the open circuit and short circuit tests. These give us two different characteristics, which we can see just in the green highlighted box. And I guess the main things to point out here is we use the open circuit characteristic to determine the voltage according to the field current. So that is the voltage at the terminals, which in our open circuit is going to be equivalent to EA, which is our excitation at the armature. And the short circuit test, we're determining the current going through the armature, so IA versus IF. All right. We can combine them to give us a few more pieces of information. And I think that moves us very nicely into the short circuit ratio. A little teaser for what's to come in a special question is your short circuit ratio. It's mentioned in the slides. It doesn't give any actual bonus information other than the fact that it is equivalent to the reciprocal of the per unit value of the saturated synchronous reactance, which is, it's a lot of words, but trust me, they sometimes come into handy, okay? But that is that. As we saw with some of our DC machines, we have a steady state equations where it's just, okay, here's our excitation, here's voltage at the terminals, here's the relation with respect to the current in the armature, as opposed to, well, yeah, current in the armature, yeah. Voltage regulation as per usual, considering full loads, and we have the phasor diagrams. So, these phasor diagrams, they assist us in, I guess, talking about where is excitation with respect to the terminal voltage. So we can tell that with overexcited machines, the excitation is of a greater magnitude than the terminal voltage. So one way you could think of this is your IA is actually contributing further towards your EA, whereas in the underexcited, it's actually contributing against. So yeah, it's just how phasors relate. Moving forwards, more power, but it's with respect to sine delta. Delta being our torque angle. It follows a number of angle names, but typically that is just the angle between our terminal voltage and the excitation voltage. Reason being, I might just draw a little diagram off to the side. You have two machines, which I'm just going to draw their phases over here. So we can imagine, okay, here's the three phases. Oh, maybe this is... there's better ways to draw it. Let's think about it slightly differently. It's very similar to how we did the lab. We had a north and a south. This is what is being rotated at the rotor. And then your armature is generating a field to try and match this, okay? Your armature might be a little lagged, and it is trying to match what is being generated, okay? So we end up with an angle difference, which we call delta, and that corresponds to the voltage between your, the phase difference between your voltage at the terminals and your excitation of your armature. Yeah, you can also relate it as a physical angle of the, in the same way that induction machines have slip, your synchronous machines have this delta angle, which I like to think of it as a phase slip, where the distance difference, which is delta, is somewhat proportional to, okay, how much of a field impact, how much of a field force is being exerted on your rotor, or in this case, the armature. But it's the same thing. So in the same way that with an induction machine, if I had omega m, omega s minus omega m on omega s, I might consider it in the same fashion. I have, okay, the theta of my rotor minus the theta of my armature on theta of my rotor, where these are, okay, the phase relative to each other is being considered here. But don't use such an equation. This is just for, I guess, a little bit of a conceptual understanding of where is the force coming from, how might we relate it to induction machines. Anyways, let's go ahead, push a little forwards. Something to note is, yes, synchronous machines, they are synchronous. And so, the torque speed characteristic is just along the straight line of the speed. If we were to have any slipping, like actual speed slipping, jumps out of an electrical degree, electrical rotation, it would mean that, okay, my north-south are over here, I'm lagging behind, and then suddenly I'm being pulled towards the opposite direction as opposed to where I was initially going. So my pushing forwards and pulling backwards end up balancing out after a single slip, and that would cause a trip back down to zero speed because there would be a net zero force applied. All right, let's try and move this. Yeah. Okay, good stuff. Something to note is that our torque and our power are somewhat, well, they're directly proportional, and they're related through delta. Now, moving forwards, because of this fact that a synchronous motor has to operate at synchronous speed, it is not self-starting. So, just something we might typically say is that the generated torque at 50 Hertz is simply not enough to spin the motor immediately. So it's too quickly to move the rotor. So it's not self-starting in a different sense to how a single-phase induction machine is not self-starting. Single-phase, it's only vibrating. Synchronous, it is rotating, but it's rotating too fast to actually catch it. It can't catch up within a rotation. So it slips, and then it yanks it backwards, which contributes to a net zero torque. All right. So there are a number of startup methods. The one that we use in the lab is we pretty much just we make it into an induction motor by running it using a separate field until it runs up to synchronous speed. Once it hits synchronous speed or near synchronous speed, we flip it over to a synchronous machine and it matches. That is how we add a starter to it, but yeah, all right. More equations, more phasor diagrams, torque power characteristic. Sorry, this is the delta power or delta torque characteristic, where we can see related sinusoidally, we have maximum torques on either end. Personally, I think it's a little silly to include the extremities of this graph, just because if you were to ever hit that kind of portion, either it's because there's been a small, I guess, deflection of your motor in an instant, where, okay, rather than being a fixed phase away from the field generated phase, you get knocked back physically by a certain amount, and then the torque would still be able to bring you back to a certain phase difference. But other than that, if your system is requiring more torque, or rather it's consistently dragging it greater than the maximum torque supplyable by the synchronous motor, then, as we mentioned before, we trickle out of synchronicity and return back to zero. If you did this in the lab, you would have heard a little bit of a bang as the machine realizes, wait, it's not synchronous anymore. Quickly turn it back onto the induction machine, and your lights would have started moving again. All right. So yes, we call that drops out of step, and we experience torque power fail, torque power fall. Give it a sec. Yeah, torque power fall. All right. The effect of field current, IF, it directly changes our excitation. However, our power of our machine remains rather constant. It is Q, our reactive power, that changes with the excitation. So how might we think of this? If we have a low excitation, there's less torque, it's going to be lagging more, and therefore we get a lagging power factor. If there is a very high field current, then we get the opposite effect. And that is how we consider that. All right. We have some power factor correction schemes that we can apply to, I guess, make it a bit more, not necessarily efficient, but it's power factor correction as per 2134. So we've seen power factor correction a few times, matching up your Qs to get a nicer system. Note that you can have certain motors, synchronous motors, pretty much acting like a capacitor. This is expressed in one of the past papers, I believe, where Georgios asks us the question, oh, but our friend Brian wants to do it with induction motors. Explain why they're wrong. It's very much just different modes of operation. But moving forwards, let's go ahead and jump straight into a question. How about that? This is the 2021 final exam question 4. This one worth 25 marks, so a solid quarter of the exam. It was all about synchronous machines. And you can see there's 2 large questions in here, which are somewhat similar to, I believe, what was in the quiz, but not completely the same. Those 2 would be parts B and C. But let's just have a nice run through it all. So, question A, it asks us to, using appropriate figures and diagrams, explain the issues with starting a synchronous machine as a motor. All right. So, we ran through this a little bit, running through the content, and main things to consider is just, okay, it needs to run at synchronous speed. It wants to move too fast. So, synchronous, far out, I can't write. Synchronous speed. It can't be caught up to in a timely fashion. And what I mean by that, it can't be caught within a rotation of the field poles. And to put it quite a bit more frankly, the machine is not self-starting. Due to slippage, a net zero torque is experienced. All right. Now, what might be some figures and diagrams we might be able to consider? Well, you could potentially look at this torque power angle thing and reason with yourself, oh, surely I'm taking control systems at this point in time, and therefore I understand that, okay, for an immediate beginning of torque, there is some kind of reference to speed with respect to the derivative. That means that my initial torque, my starting torque, to actually bring something up to speed within time, because remember, mentioned we have a time frame for us to catch up, it would need something rather significant, which would push it into power falling, torque fall. Other diagrams we might be able to apply. I mean, we could just simply supply our torque speed characteristic and say, oh, but it's at 0 speed. It's not on there. But yeah. All right. That is 4A. Let's look at 4B. Now, 4B, we have 500 kilovolt amps at 480 volts, 50 hertz, star-connected synchronous machine with a rated field current of 10 amps, and it was tested in open circuit and short circuit tests for a field current of 10 amps, so it's running at the rated field current. The measurements were as follows. For the open circuit field line voltage, open circuit voltage and field line voltage, the line current, and we're given one more piece of information, which we're going to take as a DC excitation of the armature, so a DC test as well. So we've got all three tests just sitting here for some information. Let's go ahead and find the armature resistance, okay? So armature resistance, as we saw previously, armature resistance, big thing, doesn't really change too much with the skin effect, so DC test. So 1 RA DC test. Now if we were to think up the DC test, what we get is, okay, voltage over your terminals divided by the current through that gives you your measured resistance. Remember, this is, in fact, let's get the board back. This is, in fact, a star-connected machine. When we run this through the terminals, we're running it through two sets of RA. And we're supplying a DC 20 volts, and we're getting 40 amps through. So 2 RA equals a half, RA equals a quarter. So RA is going to equal, just equal 0.25 ohms. Fantastic. That's 3 marks right there. Next question. It's a little less nice. We have to find the synchronous reactance. Now, how do we do that? We have to consider just the way that our open circuit and short circuit characteristics, what information do they give us? Something that I will be including on my cheat sheet will be right over here. Combining the test results, we just get very nicely our XS, our synchronous reactance, is equal to EA on IA from our open circuit and short circuit. Note that this is, in fact, for a fixed field current, so for the same field current being 10 amps, we get these two measurements. Very important thing to consider, because we need to go ahead and make sure we're actually gathering data from the correct points. Now, if we run back to the question, here we are. We have part 2, trying to find XS. Note that this is for unsaturated. Something that we might note is this is indeed the unsaturated synchronous reactance. And how do we think of this? Well, in the operable range of the synchronous motor, and for these tests where we run voltage to 125% and current to 150, we end up with our short circuit characteristic, something of a straight line along here, and our open circuit characteristic, which behaves somewhat linearly, and we tap it somewhere here for IF, for our rated. Okay. We notice that there is a linear behavior between these two, and that's not for no reason. We like sticking things in the linear region for rated purposes, as we discussed previously a bit with transformers, but that is that. So we know that this does indeed give us excess unsaturated, which is going to be EA open circuit characteristic on IA short circuit characteristic, which if we run back to the numbers, I believe was 490 on 420. But remember, this is all phase related rather than line related. So we need to divide our 490 by root 3. I believe that was 490, yep. And then divide all by 420. This will give us about 0.674 ohms. And we could say per phase, but that is that. Question.
You used EA as 490, but the open circuit voltage is VT, right? So why are they the same?
All right. So we have an open circuit voltage here. And so let's get this back. When we run our test, we have our EA excitation, we have our resistance RA. This is all on the armature side. We have XS, and then we have our terminals. And just for the open circuit test, we leave these completely open. Having no load means no current, and therefore no current means that VT equals VA. Sorry, not VA, EA. Something to note here as well, this is the EA given a rated field current. Oh, it's going to throw everything. This is the EA using a rated field current, and therefore we have our rated field. Oh no, I'm actually losing my mind with this. Okay. Worst case. But yeah, this is our EA, that is our generated excitation voltage throughout the rest of our testing, and for any considerations with a full load. All right, so that is that. Fantastic stuff. Let's move on to question 3. Question 3, we want to find the saturated synchronous reactance. All right, so XS saturated. Now you'll recall previously that we mentioned that the short circuit ratio? Yeah, the short circuit ratio, while not mentioned explicitly in our notes, it's mentioned in Georgios's notes. The short circuit ratio is actually the reciprocal to the per unit value of our saturated synchronous reactance, which is what we're trying to find. So how do we do that? We'll just say the per unit value is going to be equal to the reciprocal of the ratio of the, this was in the quiz, the ratio of the field current to the open circuit voltage, and the ratio of the field current to the short circuit current. Okay, so we get the reciprocal of our, remember we're working on a somewhat linear scale over here, so 10 times we need to get to our rated voltage. Our rated voltage of our excitation is 490 as opposed to, sorry, our rated output is 480 as opposed to 490, so we need to multiply by 480 on 490. This ratio to the current to get a short circuit. Typically with 10 we get 420. Instead we need to get the current, the rated current for the armature. How do we get that? We get that using the power. So recall that power equals root 3 VI asterisk. So mind you, this is line to line. We end up with I line to line is going to be equal to P on root 3 VLL, which is 500K. Yep, 500K on root 3 times 480. All right.
So that's complex power?
Yes. Yes, it is. All right. So, moving from there, what do we get from here? We end up with, I'm just checking my notes, I believe it's 601.41. So 601.41 on 420. Is it 420? I believe it is. Yes, that is our line current. So this is what we used to determine the saturated per unit value of our of our armature reactance, the synchronous reactance. It's a little out there, and when we perform this, we end up with about 1.4618. Now remember, this is ohms, actually, this is just per unit. If we wanted to convert it back into ohms, what I might suggest we do is take it with respect to, I'm actually unsure.
You can find your base impedance from,
Yeah.
because we're given line voltage.
We are given line voltage and power. That is a very good point. We can find our base impedance. So, base power is given as 500k. Base voltage is given as 480. And therefore, to find our base impedance, we just take the base voltage squared on the base power, which will give us a number. It does need to be per phase. That is true. So I need to multiply by 3 or divide by 3. What do you reckon? I'm pretty sure it's multiplied by 3.
You need to divide your power by 3.
Let's just P on 3V squared, sorry, P on 3 equals V squared on R.
And your voltage right now is line, so that needs to be
R equals 3V squared on P. Yeah?
Is that line voltage or phase voltage?
I mean, if we're using line voltage, we end up with it working anyways, because we get a root 3 in there that gets squared to give us just a 3.
So
They might cancel. I think they cancel,
yes,
because this is a line to line. All right, perfect. Wow. Okay, let's jump on the calculator, and we're going to get a number that might be close to 1 or 2. So 480 squared divided by 500k, 0.4808 ohms. Fantastic. Let's multiply it by 1.4618. And you're never going to guess. You're never going to guess. 0.6736. As a little dummy check, you might be able to go ahead and consider, okay, here is our unsaturated value, here is our saturated value. Are they meant to be different? Typically, yes. As we saw previously, we get something of a tan inverse relationship between the current and flux of machines. And so when magnetization hits and we hit saturation regions, we end up with larger shoves. Recall, just like, this is something of a linearization of systems where we just consider, okay, well, along a straight line, I should have one kind of impedance. Along different straight lines, I get different impedances. So I might be considering a straight line from here to here as my impedance line for my for my saturated XS. But yeah, all right. So if we're getting more flux for, I think I did this the wrong way around. This is meant to be phi versus I. Lots more current needed for a little bit more flux. That's more like it. By needing more current for the same kind of voltages or just a small increase in voltage, we need a smaller equivalent impedance, and therefore it does make sense for this to drop down when we look at the saturated version. All right, that is that. Next up, this question has 5 parts. Sorry, this sub-question has 5 parts. Part 4 is draw the common plot of the short circuit characteristic and the open circuit characteristic tests and explain why 2 different values are used for the reactance. So you'll actually find we just did that right here. Now, 2 different values for the reactance. As we mentioned previously, it's all about the potential saturation of the system. So unsaturated, we kind of just assume that our values are going along a linear region of the curves. However, to consider a saturated version, we need the short circuit ratio. So we're pretty much doing 2 completely different calculations where we're considering 2 different circumstances. We understand that for the rated current and rated voltage, we might be moving into the edge of our region of linearity. However, for some of the tests, as in for some of the tests at the rated current, we might be within the linear region. So we're checking out different regions of our characteristics. So looking further beyond, maybe to over here, where we see non-linearity in the system, where we experience some saturation. And I believe that is air gap saturation, saturation because of a lacking air gap or something. You would increase air gap to decrease saturation. Anyways, all right, good stuff. That is B. Sorry, that is 4, part 4. Part 5, draw the equivalent circuit of the synchronous machine. As we saw previously, Georgios loves these trivia questions. So we get a resistor. This is our RA. It can also be tuned using an adjustable resistance. And then we get the inductance here, which we call X. Sorry, that's not meant to be RA, RF, and XF. So these are just purely for our field, typically with some kind of DC excitation. So I'd say VF, which typically DC. So this is our field circuit. And then for the armature circuit, what we would do is we would go ahead, we have a generated excitation, we have our resistance of the armature, and we have the reactance, which we might tap into a load. All right. Wow. Only into the next part of the questions. All right. That's the 15 marker out of the way. Onto the 7 marker. We have part C, where, I mean, it's 2 parts with another question. No, it's just 2 parts, my bad. So we have a 15 kilovolt amp, 400 volt, 50 hertz star connected synchronous generator that supplies 50% of its rated current at a power factor that is 0.9 lagging. Armature resistance is 0.5 ohms and the synchronous reactance is 10 ohms. So this is giving us quite a bit of information. We know all the power stuff. We know our entire armature resistance. Let's go ahead and find out what the torque angle is at half power, rather half current. All right, so let's do this. Let's determine the rated current first. So rated current, we need to do P equals √3 VI conj. So we end up with, I'll use S here as opposed to P so we don't get confused. we get I conjugate is going to be equal to S on root 3V, which is going to be, if we assume rated voltage and such, because we are calculating rated current as of right now, 15 K on root 3 times our voltage, which was 400. And we need an angle. The angle is going to be given by lagging 0.9. So we say cos inverse of 0.9. This should give us a number. Give me just a sec. Let's calculate it. All right. Root 3 times 400 angle of cosine inverse 0.9. This gives us 19.486 with an angle. Oh, damn it, my calculator is set to rectangular. That's more like it. 21.65, angle 25.84 degrees. All right. Recall that this is the conjugate of the current, so we would just need to flip the angle. And now we go ahead. We want to determine the torque angle, so easiest way that I find to do this, we're going to compare the terminal voltage to the excitation. So typically we go ahead and say, okay, as a reference, V, which is our terminal, is going to be 400 on root 3, which is our line to line, we're considering phase, and it has an angle of 0. Okay? We want ET now, sorry, EA, and because this is motoring, we have VT plus IA ZS, all right, with all the phases included, which will be 400 on root 3 plus, recall we're operating at 50% power, so, sorry, 50% rated current, so we're going to half this current to give us, I don't know why my calculator is still set to rectangular, that's a little silly. 10.825 angle 25.84 degrees negative, which is now going to be multiplied by 10J plus 0.5. Now, as a little dummy check, let's consider this is pretty much just going to be 10J. If I check on a 10J, I get an angle of 65-ish, and then I'm adding on big constant, I should get around 10 or 20, okay? As just a little dummy check, let's go ahead and perform this calculation. So 400 on square root of 3 plus 10.825 with an angle of minus 25.84. J plus 0.5. All right. And in phasor form, I get 298.535 with an angle of 18.57 degrees. All right. Fantastic. So, by now comparing the angle of my excitation and my terminal voltage, I get a delta of 18.57 degrees. All right, good stuff. Any questions so far? Please do ask. All All right. And then they want us to determine the theoretical maximum value of the torque angle of a synchronous machine. So we want to determine what are the issues with operating close to the maximum torque angle. So I'm going to do that just over here. All right. So as we mentioned previously, if we're clocking a little bit past that 90 degrees, as we saw in the torque delta graph, if we clock past it, if a system needs more than this torque, well, afraid to say that the synchronous machine cannot supply it. It can't supply it, so what does it do? It falls back down to zero. Torque fall. Spins out. So, what do we say? 90 degrees. Do we just say 90 degrees? Not technically. So, something to note is this is an electrical angle. It's not necessarily a mechanical angle. Our mechanical angle is simply when we look in between. I'm going to use an 8-pole system to consider. North-south, 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 north-south. If I am directly in between a north and south pole, and I have my north pole here, it wants to move away, it wants to move to. This is the maximum pushing that I'm going to experience here. It relates somewhat sinusoidally, so I have minimum pushing when I'm at my south pole, because I'm already there, there's no need to push further. There's also a minimum push near where my north pole is, because it doesn't know which way to push. Coming to a maximum, just in between. So, we see a maximum directly in between. In terms of electrical angles, this is 90 degrees. Mechanically, you divide that by the number of poles on 2, so number of pole pairs, in this case 4. So, that would be like 22? That sounds correct. 22 degrees. 0.5, yes. Well, yeah. Yes. So that is that. So 90 degrees electrically. The reason being we want to avoid pushing it to such a large torque angle, why we don't want to operate near it, is to avoid torque fall. We don't want our motor to stop working, right? It gets pretty costly because then you would have to continually start it up and constantly use either a induction machine as a backup, and at that point, what's the point of using a synchronous machine? Just give it more voltage. Yeah, all right. Thank you guys very much. That is pretty much that for the checklist. Georgios had a number of knowledge checks to help us run through what might you want to double check before going into the finals. We have knowledge checks for topic 2. All of these will include conventions and terminology, so please make sure you can read the questions. Probably the best start to going into an exam. Some things I might note. I mean, learning from the midterm, Georgios loves his trivia. So if you reckon it's impossible for him to ask a question about voltage regulation, just bite your tongue on that. But yeah, it's that. So feel free to grab these slides from either the ELSOC drive or from the QR code at the start. And yeah, best of luck, everyone. Thank you for coming.
Did he say what is it really going to be 3, 4, 6, 5? No, 3, 4, 5, 6. Or? Yeah, 3, 4, 5, 6.
3, 4, 5, 6. 2
Yeah,
is for our fundamentals. 3, 4, 5, 6 content. Yeah. Fantastic. All right.
You sure there's not going to be a final exam question on what the percentage of coal-generated power is in the circuit?
I think they'll get us to approximate Reynolds number. But no, it's, yeah.
What was that comment in regards
synchronous. So, yes, I mentioned it's interesting because for the rest of all the diagrams that Georgios has given us, he only goes like the per phase equivalent. But for some reason, he thought, I need to tell them this time. If it's unbalanced, then you need to consider all three different circuits, which could be a little silly with, I don't know, maybe he wants to do something where he taps it a little. Well, it depends on how they're connected at the load side. So whether it's, if it's a Y connection at the load side, you'd imagine, okay, there's some manner of neutral, but then that means you would need to do a massive nodal thing where you go ahead and, okay, there's a actual voltage here rather than just 0. Otherwise, if it's delta, I mean, yeah, you'd have to do manual nodal as opposed to simplifying to the per phase equivalent because you can't be certain that, okay, this is 0 volts. No, you don't know that. Yeah. But it's
I don't think it'll come up. Like,
surely not.
we only learn balanced load.
Yeah.
Was there any tutorial question?
No.
How can
It'll be okay.
I mean,
Doing like a smiley face.
there'll probably be like maybe a bit of understanding.
Mysterious second page.
There might be an understanding question on it. Just like, oh, what if I change just one of them to however many ohms? But yeah, just understanding what might happen to the system. Funny harmonics, yeah. So, some things to consider going into the final exam.
Where do you is this available with all the annotations? It just helps me jog memory on this.
With annotations,
We can do it now.
we can do that now.
We're chucking
Yeah,
it in
it's
the
all
same
good.
spot on the drive. So the link's in the stream. Also, the QR code's at the top of the slides.
Okay, it's in the stream. Okay, thank you very much.
All good. Thank you for coming.
I mean,
Is stream ended?